Chapter number 8, covalent bonding. So what are we going to do in this one? Since we have discussed it before, covalent bonding is all about non-metals combining with non-metals. So when non-metals bond with non-metals, they actually form covalent bond. Now, why does that happen? Previously in the ionic bond, the electrostatic attractive forces were between something positively charged or something negatively charged, which was all occurring due to a simple phenomenon. Positively charged lost an electron, and the same electron was gained by a negatively charged species. I mean, an atom which was later on converted into a negatively charged species. So this was transfer of an electron.
Mm.
That's one fact, by the way. And there may be other options. For example, in covalent bond, a pair of electrons is shared equally between two atoms. Means every atom contributes one electron each, and a pair is actually shared. What holds the atoms together is the strong electrostatic attraction forces between nuclei of both atoms. So they form a bond by the shared pair of electrons. So the attractive forces are in between the nuclei and the shared pair of electrons. All right. So
Mm.
when it comes to that, I actually tend to come up with an example. So in order to quote an example, can you tell me the name of your best friend, if there is one?
No.
Come on, come up with the name of any of your class fellows, anyone.
No.
Come on, give me any girl name.
No.
Hypothetical.
Yeah, yeah. NOUF.
Oh, I thought you're saying no. Okay. So that's no. All right. So NOUF, as you stated. Now, let's assume let's assume that you have a cafe and that cafe has a $100 heavy burger, and that burger is equally loved by Manal and Noor. All right. Let's assume that the pocket money that Manal and Noor get is $50 each every day. Now,
Yeah.
what are the options that Manal and Noor can opt in order to get that burger from the cafe? Now, the first option is Manal gives all her money to Noor. Noor goes to the cafe, buys the burger, does not even put a kind look towards Manal. He eats the whole burger in haste, and Manal stays in loss. So, loss of Manal, gain of Noor, right?
Yeah.
That's the first option, right? One of you loses, one of you gains, right? So,
Yeah.
the opposite may occur. That is another option. So Manal might gain from the loss of Nof. Nof actually gives her $50 to Manal. Naz goes to the cafe, buys her favorite burger, eats the whole burger without even giving a kind of look to Nof, and afterwards take a break. And she finally has the self achievement of gain. In that case, sorry, that's actually Manal, and
Mm.
Nof loses, right? This is
Yeah.
one of your options. The second option is equal sharing. You both have 50 rupee, $50 each. You both go to the cafe. You buy $100 burger. You get it cut in exact half. You sit
Mm.
together at a table. You enjoy your half equally by chatting with one another. Equal sharing,
Yeah.
right? Now, let me tell you, this was ionic bonding.
Yep.
This is going to be covalent bonding. We actually act like our atoms do. That's why I'm going to give you an example. And I'm going to extend the example a little bit to a
Mm.
point where this example becomes fun and learning at the same time. So far, it's a little bit
Yeah.
boring. So let's convert it into a good example. Now, third is that whole class pulls in, right? This is something that we do on trips and tours. when we are going for an extracurricular activity. Let's suppose we're going to another city or another country. Everybody in the class pulls in, everybody enjoys, everybody has the burgers and stuff. They go to different places, they eat different kinds of traditional or classic foods of some other country, and everyone enjoys. All right. When
Yeah.
the whole class pulls in and whole class enjoys, right? That is the kind of bonding we're going to study in metallic bonding.
Oh,
Now, these
okay.
are pretty steep options. One loses, one gains, equal sharing, whole class pulls in, everybody enjoys. These seem like little filmy, right?
Yeah.
So, in actual life, there are many other incidents. Let's think of a one, all right? Let's say that the whole thing started with the idea of equal sharing. Manal and Nof agreed for equal sharing, went to the cafe, bought the burger. Along with the burger, they requested to give them a knife. Then they came back to sit at a table. When they sat at the table, Manal thought, I'm stronger. Why don't I keep a bigger piece? In the end, if we ever fight, I'm going to give a punch to Nov, and Nov would quickly would be down to the floor. And there you go. I can be always a winner. Or even if it doesn't turn to a fight and I just give her a good, strong look, and she's going to step back, I can easily keep the bigger half. So, what happens? Manal, even after they are agreed on an equal sharing, actually tries to keep the bigger half and succeeds
Mm-hmm.
by
Oh,
giving her an angry stare. You can't do nothing to me. I'm gonna keep the big piece and enjoy it. Yeah,
yeah.
one of the scenarios that you might ever face in life. I hope that doesn't happen to Manal and Nov, since this is just a filmatic scene that I'm coming up with. But let me
Yeah,
tell you,
yeah.
this kind of bonding does exist.
Oh,
Okay, let
yeah.
me tell you one more thing. Manal and Nov agreed for a gain and loss. So Manal agreed for a loss. Manal gave her $50 to Nov. Nov agreed for a gain. But when Nov went to buy a burger and she was enjoying it, she had a kind thought about Manal, and she thought, why not I share a little piece with Manal? And although they both agreed for a loss and gain factor, they actually shared a little part of that piece. That kind of bonding, that kind of action exists in Atom. All right.
Yeah.
Although it was
Yes.
supposed to be unique, but it showed a little bit of a sharing character, which was covalent. And in the
Mm.
previous example, although it was supposed to be covalent, but it showed a loss and gain character, and Manal thought about simply her bigger half. So that was actually right of some ionic bonding in the covalent bonding. Let me tell you, bonding mixes with one another, but that's about actually a part of A level. Any
Mm.
scenario that you can come up with in case of bonding that actually happens between the atoms. I keep saying something to my students that we behave like our atoms do, or our atoms behave like we do. So it's pretty similar to one another. I usually come up with this example in class, and it's pretty funny when I'm doing it in the class, but when I'm doing it with a single student, it's not as funny, right? Um,
Yeah.
One last thing, there is always a chance for donation. Donation is something that we give away and we never ask back anything
Yeah.
in return
Mm.
for it. This also exists in mourning.
Oh,
So donations, even when you agreed for loss and gain, you still shared. Even when you agreed for sharing, you kept the bigger half. All of these exist in bonding and will come as a part of A level course. So far, we are just going to stick with these three scenarios in your book at
yeah.
IGCSE level. All right.
Mm. Yes.
So keep that stuff in mind. So what we're going to do this time is that we're going to go with sharing. All right.
Yeah.
This chapter is all about equal sharing. And what are we talking about? We're talking about sharing of electrons.
Yep.
So two atoms are going to share electrons. Previously, an atom used to give an electron, and we used to draw an arrow from one atom to another.
Yeah.
because the electron was transferred to one from another. When we talk about sharing, what we actually do is that we overlap circles. The circles are not properly overlapped. If I properly overlap, this would be something like it. And we draw
Yeah.
the electrons inside that overlapped part to show you how they were equally shared. And whenever I use the word equally, I am actually trying to prove to you that if one atom shares one electron, the other one is bound to share one electron as well. If one atom shares two electrons, the other one will also share two. That's why I'm calling it equally all the time, though that word is not exactly used over here, but I'm using it for a purpose that you understand the point.
Yeah.
Make sense?
Yes.
Okay.
It's
All right.
also this is also there in maths, right? Like Venn diagram.
Yeah, Venn diagrams also are about the overlapping of circles.
Yep.
But Venn diagram is a lot more than just overlapping of circles. Venn diagram is sometimes about a circle inside a circle, bigger and smaller circles, and areas about those. Venn diagrams have a lot of perspective apart from just overlapping of circles. Now, now consider two atoms. What we're gonna do is that we're gonna consider two same atoms. Let's uh, consider assume the fact that they share an electron pair between one another. Now, this shared pair of electron is attracted to nuclei of both atoms. We usually draw this diagram to give students the idea that attractive forces are dominant over here. Why do we explain this stuff? Now, students usually tend to say, if I'm going to draw a bigger form of this circle, if these are two electrons, you understand this one is negative, this one is also negative, and you'll find the small negative signs drawn in these circles as well. Now, students tend to ask, since these both are negative, they're going to repel one another. So, how can you form a bond with such kind of repulsion in between?
Yeah.
So, I explain my students that there is only one repulsive force between these two particles, right?
Yeah.
So, this atom is going to attract this electron, this atom is going to attract this electron, this atom is going to attract this electron, this atom is going to attract these electrons. There are four attractive forces with every one repulsive force. So which ones are going to dominate, the attractive forces or the repulsive forces? Of course, the attractive forces, right?
Mm.
Since they are so
Yeah.
high in number. I assume you were about to answer four and I kept on talking. Is that right? Sorry, I was actually in a phase. I never thought that you might answer the question. Okay, so
Yeah. No
I hope
problem.
you understand that the attractive forces are going to dominate and a bond would form. So much so that bond would keep both the atoms close. This example is good enough for a covalent bond in hydrogen molecule. Every hydrogen atom has just one electron in its outermost shell. We draw one of the hydrogen's electrons as dots and
Yeah.
one of them as crosses, and we actually put them at the exact overlap portion of both the circles. You can
Mm.
either draw it like this, that both of them are the same line, and on the line you draw a dot and a cross, or you may draw it like this, overlapped, and you can draw them inside the overlap to show the
Uh,
bonds. So whether you do it like this or you do it like this, both of these are considered as correct.
mm.
This is
Okay.
hydrogen molecule. This is formed from two hydrogen atoms. We call them as diatomic molecules since they are made up of two atoms. The formula is H2. They are joined by a covalent bond in which both hydrogen atoms actually share one electron each and make a very strong bond.
Mm.
All right? Make
Yeah.
sense? Good. Let's move on. Remember that although the electrons are drawn as dots or crosses, there is absolutely no difference between them in reality. The dots and crosses simply show that the electron comes from two different atoms. So it's actually your ease of understanding because of which we are drawing a dot and cross, not because the electrons are different from one another.
Mm. Okay.
So the significance of noble gas structures in covalent bonding. Now, every covalent bond that forms is forming in the drive of getting stable. Atoms are not stable. They have different number of electrons in their outermost shell, and most of them are not stable in the periodic table since they don't have a complete outermost shell. And when they don't have a complete outermost shell, they actually share the electrons in order to have a perception or have a feeling of like a complete outermost shell or stable outermost shell. Who have the stable outermost shell in the entire periodic table are named as noble gases. So what actually every other atom is trying to do is to copy their electronic structure by bonding.
Hmm.
For example, hydrogen atom has only one electron to share. When it forms a covalent bond, the shared pair of electron is in the outer shell of hydrogen. This is the exact same number of electrons as the noble gas. The nearest noble gas to hydrogen is, that is, helium. So both the hydrogens actually tend to have a covalent bond because then both of the hydrogens will consider that they have two electrons each. And two electrons is, to be honest, is actually the noble gas configuration of helium. So both hydrogen atoms become stable because they have the noble gas configuration of helium gas, electronic configuration of helium gas.
Hmm. Okay.
So every element is going to do the same. Now, let's discuss how they're going to do it. And we definitely need the periodic table to do that. So I'm going to scroll a few pages till we get to the periodic table chapter. Now, I'm taking you back to the periodic table because I want to explain a simple fact that covalent bonds are made up of nonmetals, and nonmetals that you see over here are all drawn in yellow. So there are
Hmm.
very little nonmetals over here. So
Yeah.
this is the first one that we started off our example with. Hydrogen combines its electrons to get the noble gas configuration of helium, the nearest noble gas to it. All carbon, nitrogen, oxygen, and fluorine are going to gain the noble gas configuration of neon. So silicon, phosphorus, sulfur, and fluorine will try to take the noble gas configuration of argon. How would they be able to do it? Now, let's take the example of fluorine first. You have fluorine over here. How many electrons are there in the outermost shell of fluorine?
1 second. Just check. Chlorine.
You're sitting in front of a periodic table. What are you working on? Remember, the number of outermost shell electrons is equal to the group number, and you have group numbers written on this periodic table. So, what will be the count of outermost electrons in case of
10.
fluorine?
7.
7. Now, how many electrons do you need it fluorine needs to share to get the nearest noble gas configuration, which is 8 electrons?
1.
Great. If we go with the same pattern, how many electrons do oxygen need to share in order to complete its octet, have 8 electrons in its outermost shell, and become stable?
2.
What about nitrogen?
Nitrogen.
It's in group number 5.
3.
Great. What about carbon?
Carbon. 4.
I hope you understand it now.
Yeah.
So, what about bromine?
I mean, 5.
Sorry?
5.
Bromine, Br. It's right over here.
Oh, okay.
That is boron, just B, not Br.
Oh, yeah, yeah. Okay. So 1.
1. So now you understand. As soon as you look at a non-metal, as per its group number, you know that how many electron it has in the outermost shell. The whole idea is about the fact that it is going to share as many number of electrons as it needs to get the stable octet or 8 electrons in its outermost shell. That's the really simplest of ideas to explain how they bond and why do they bond. So they bond by sharing of electrons, and why do they do that? To complete their octet, become stable. To
Yeah.
have the configuration of the nearest noble gas. It was the same concept that was taught back in ionic bonding. So we're
Yeah, yeah.
actually spelling out the same thing over here. This rule
Okay.
is known as octet rule. For hydrogen, duplet rule applies, 2 electrons in its outermost shell. For all other nonmetals, that's 8 electrons in the outermost shell. Noble gases do not react because they already have a complete octet or 8 electrons in their outermost shell. So it's pretty easy. All right. So
Yeah.
now you know. So why does hydrogen form molecules? It needs to become stable. It is not stable with 1 electron, but as soon as it is going to share one more electron, a duplet will complete and it will get the noble gas configuration of helium, right? So
Yes.
covalent bonding in a hydrogen chloride molecule. The diagram is given right over here on your left. What does this diagram tell you about this covalent bonding in hydrogen chloride molecule? Hydrogen shares an electron. Why?
Okay, so I think chloride shares. No, one sec. Yeah, yeah, yeah. It shares one electron to hydrogen in order to be two.
Good. Hydrogen shares an electron because it wanna be two, the configuration of the nearest noble gas, which is helium. What about chlorine? It also
Chlor.
shares 1 electron.
I didn't understand the question. Can you just explain what you're asking?
So just like you answered me that hydrogen wants to have 2 electron in its outermost shell, so it shared one. And
Yeah,
hydrogen now has the configuration of helium, the nearest noble gas. In case of
yeah.
chlorine, it shared an electron because then it would have 1, 2, 3, 4, 5, 6, 7, 8 electrons in its outermost shell, which is the nearest noble gas configuration of argon.
Hmm.
So, to be honest, chlorine actually completed its octet, 8 electrons in its outermost shell, and hydrogen actually completed its duplet, 2 electrons in its outermost shell, right? And that's how hydrogen becomes stable as well as chlorine did. Make sense,
Mm-hmm.
right? That's what's
Yeah.
happening over here. And the
Okay.
same thing is explained right over here in the parts where they consider actual configuration and discuss the same thing about it.
So they just share electrons to be stable, right?
Yes, actually, the whole bonding is about stability, whether it's loss of electron or gain of electron or sharing of electron or pooling in all of their electrons, it's actually all about stability. Atoms
Mm.
like to have either full electron shells or at least 8 electrons to become stable. And that's why the whole bonding occurs.
Okay.
Make sense?
Yes.
Good, good. Now, since the covalent bonding also occurs in the outermost shell, just like ionic bonding, so inner shells will not participate in covalent bonding, right?
Yeah.
Let's move on. Next example is of covalent bonding in chlorine molecules. Diagrams are right there. So now you know that chlorine has 7 electrons in its outermost shell, and chlorine just needs 1 electron in sharing, and it can complete its octet, which it did by this kind of sharing. Both
Mm.
chlorine now have 8 electrons in their outermost shell. Count this one: 1, 2, 3, 4, 5, 6, 7, 8. Count the other one: 1, 2, 3, 4, 5, 6, 7, 8. Remember, these two electrons are known as common or shared pair. These
Yeah.
electrons are actually common for both the octets. And that's how octet or 8 electrons are completely there and stable inside the structure of each chlorine atom.
Yep.
Okay? Good.
Yeah.
So covalent bonding does happen in methane or ammonia or water. And for those structures, methane consists of carbon, ammonia consists of nitrogen, water consists of oxygen. They're going to show you how that happens. Take a look. Carbon has 4 electrons in its outermost shell. So 4 hydrogen atoms are going to share 1 electron each to make sure that we complete the octet around carbon. Let's try and count electrons around carbon. 1, 2, 3, 4, 5, 6, 7, 8. So carbon has 8 electrons in its outermost shell, and that's how it becomes stable. But that's for the formula of methane,
Mm.
right? When we
Yeah.
talk about ammonia, in case of ammonia, it has 5 electrons in its outermost shell. So it tries to grab these three.
It's
Sorry, my
overlap.
bad. My bad. Actually, they were supposed to be dots, not crosses. So these three, this dot, and this dot. And that's how 5 plus 3 is equal to 8. It completes its octet. Make sense?
Yeah.
Good. In case of oxygen, let's come to oxygen. This is a different criteria. Oxygen has 6 electrons in its outermost shell, gaining just two more. Sharing just two more. It's gonna have an octet complete: one, two, three, and four. So each one has 2 electrons. So it has 8 electrons in its outermost shell, a
Mm.
complete octet,
Yeah.
which makes it stable. So that's how it works. Are we good?
Yes.
I'm going to skip the looking ahead part for now since it's not a part of syllabus. We may study it a little later when you're good with it. When you talk about covalent bonding in a slightly more complicated molecule, for example, ethane, and since ethane has 2 carbon atoms, all right? So what
Mm.
you can see in front of yourself is that the whole structure has shared electrons, so much so that all the hydrogens complete their duplets, 2 electrons in their outermost shell, and all the carbon atoms complete their octet. Let's count for the carbon atom. This is the first octet for this carbon atom, second, third, fourth, clear enough? And
Yeah.
if I count about this carbon atom, so this one is the first one, then second, then third, and then fourth.
Four. Yeah.
So that's how, with 4 pairs each, carbon atoms actually stabilize themselves by having 8 electrons in their outermost shell. All right.
Yeah.
So keep that in mind when drawing molecules containing carbon and hydrogen. It is useful to remember carbon always makes 4 bonds by sharing 4 electrons. All right. Hydrogen,
Mm.
on the other hand, always forms 1 bond by sharing 1 electron. All right. So if
Yeah.
carbon can form 4 bonds, then nitrogen can form 3 bonds. It's easier to remember this way. Oxygen can form 2 bonds. And halogens like fluorine, chlorine, or bromine, maybe iodine or hydrogen, can form 1 bond. That's the maximum number of bonds they can form in these types, ionic and covalent. All right. So keep this
Mm.
stuff in mind.
Yeah.
From here on onwards, we have multiple covalent bonding. So I would suggest that